Hi, in this video, we are going to consider a new problem solving technique that you may not have seen before. This is called the extreme principle. And we want to understand what this principle entails and how we can apply it to problems. This is going to be a short video. I'll explain the principle and then we'll look at a few examples. And that should be that about this section. So what is this principle about? So it is a method where we consider some special objects like which are either maximal or minimal. In geometric terms, they could be the longest or shortest depending on the question in order to solve a problem. So the best way to explain it is through examples, but I want to outline certain things before we do that. So you can see applications of this in geometry, in number theory, in combinatorics. You'll see applications of the extreme principle in all of these fields. But the thing to remember is you usually use this principle to prove the existence of certain objects. Prove the existence of certain objects, certain maximal or minimal objects. And some key points that you need to know are if you have finitely many real numbers, finitely many reals, then there is a maxima minima in them. There is a maxima or minima element in that set. Then another thing to notice is among infinitely many positive integers, infinitely many positive integers, there is a minimum. So if you have a set of infinite positive integers, there will be a minimum of that set. If you have a set of finite real numbers, there will be a maxima and minima of that set. However, if you have infinitely many reals, then there does not necessarily exist a maxima or a minima in that set. For example, if you take the set 0 to 1, set of all real numbers belonging to this interval 0 to 1, there are infinitely many real numbers, but we cannot say for sure which one is the maximum real number and which one is the smallest, right? However, if you have a set of positive integers, there might be infinite of them, but we know the set has a minimum element, which is 1, right? So these types of ideas will be used in problems when we consider, say, a maxima or a minima of a certain set and then try to solve problems accordingly. So let's get into the questions and we'll understand from those questions. So the first one is this one. In a round robin tournament, suppose there are n greater than equal to 3 players, and none of them win all the games. Now we have to prove that we can find 3 players. A, B, and C, such that A beats B, B beats C, and C beats A. So the question is simple. There is a tournament of n players, n greater than equal to 3, and they will play each other. It's a round robin tournament. Everyone plays everyone else. And we know that none of the players win all their games, right? We have to find three players. We have to show that we can always find three players such that there will be a cycle sort of a situation where A beats B, B beats C, C beats A, right? So how do we approach this problem? You can try it yourself, but you can pause the video and try it yourself. And if you have given it a shot, then you can look at the solution. However, we'll start by considering the extreme principle. So let's say let A be the player who wins the most games. Let A be the player who wins the most games. Now we know that since A does not win all the games, that is given in the problem itself. Since A does not win all the games, there is some player C that beats A, right? Correct. So what we have said here is we are considering the extreme person, the person who has won the most games, that is player A. And we know that player A does not win all the games, so there must be at least one person C who has beaten player A, right? Now, then consider all the players who lose their game to A, right? Great. So there will be a set of players who will lose their games to A, right? Now, what we can say is if all of these players lose to C as well, then C wins more games than A, right? You have to understand this. Let's say A defeated 4 players, B, D, E, F. Now, all of these players should not lose to C as well, right? Because if C beats all of these players, then we know that C beats A also. So that means C will have more wins than A. But actually, we had assumed that A was the player with the most wins, right? So therefore, if all of these players lose to C as well, then C will win more games than A, which is contradiction. C cannot win more games than A. Therefore, there must be a player here, let's call him B, who loses to A but wins against C, right? There must be a player like that, B, who lost to A but wins against C. So then we have our condition A defeats B, A greater than B, let's say. A defeats B and B defeats C, but C defeats A, right? This type of situation is happening. And that is what we wanted to prove, right? Now, understand that the way you solve the problem is by assuming this A person who has won the most games. It is guaranteed that there will be a person who wins the most games because it's the number of wins is an integer and there will be a finite number of integers, right? Every player's wins are integers, and if you see the set of all the integers which are counting the wins of each player, it's a finite set of integers. So there will be a maximum element to that set, right? So let A be the player who wins the most games, and after that we have this logic by which we are getting a contradiction. And this is one example of the extreme principle. So I hope you understand how we have proved it. Let's look at another question. Let's look at this one. Suppose there are 8 points in space such that no four of them lie in the same plane. Lie in the same plane. Okay. There are 17 line segments. There are 17 line segments between some pairs of these points. So basically, there are a total of 17 line segments that can be drawn between some pairs of these points. Prove that these line segments form at least one triangle. Form at least one triangle. Okay. So, okay, there are 8 points in space. No 4 of them lie in the same plane. So most of them are not coplanar. 3 of them could lie in the same plane, but not 4, right? And there are 17 line segments between some pairs of these points. Now what we are going to do here is, again, we'll try a proof by contradiction. And first of all, we'll assume an extreme element, right? So we'll say, without loss of generality, we can assume that A is a point with the greatest number of line segments containing it. With the greatest number of line segments containing it. Containing it means basically most number of line segments are passing through A. Containing it. And let n be the number of line segments that pass through it. Number of line segments through A. Again, notice that we are assuming A as the point with the greatest number of line segments passing through it. This is an example of the extreme principle again. We have assumed A as the extreme point through which most of the line segments pass, and let's say n is that number, right? Now, for the other, how many points are there? There are, okay, 1 second. Before that, we will say, if the 17 line segments form no triangles, then no two of the n points connected to A have a line segment between them. Let's try to understand this statement. So we have to prove that these line segments form at least one triangle. We are trying to assume the opposite. We are saying that if the 17 line segments form no triangles, this is the contradiction assumption, right? Then we can say that no two of the n points connected to A have a line segment between them. So what is the situation here? We know that A was connected to n other points, right? Let's say this is another point, B, C, D, E. We know that n such points pass through A. There are n line segments passing through A. Now, if any two of these points are connected by a line segment, then we have a triangle, right? If any two of the n points connected to A, there is a line segment between them, then we have a triangle including A, right? So we are saying that no two of the points that are connected to A have a line segment between them, because we have assumed that the 17 line segments form no triangles, right? We have assumed the opposite. We have to prove that the line segments form at least one triangle. So we have assumed the opposite, that they form no triangles. And now we are saying that none of the none of the points that are connected to A have a line segment between them, because then there will be a triangle, right? Okay. Now I'll just rub off some space here and we'll analyze further what happens. Excuse me. So here we will say for the other 7 minus n points. What are the 7 minus n points? Remember that we had 8 points in space. A was one of the points. So there was 7 other points and then n points were connected to A. So we are talking about the other 7 minus n points which are not connected to A. Not connected to A and not A basically, right? For the n 7 minus n points, each point is contained in less than equal to n line segments. What do I mean by that? We have said that A was the point that had the greatest number of line segments containing it, right? So A had n line segments passing through it. So the other points, which are not the extreme points, the other 7 minus n points should not have n points passing through them. It should have less than equal to n line segments passing through them, because they are not having so. A is the point with the most line segments, so others will have less line segments passing through them. So the total number of line segments in this situation will become n line segments that pass through A plus it will be 7 minus n times n. This is the maximum value, right? Why are we saying this? 7 minus n times n? Because 7 minus n will have less than equal to n line segments through them, right? So the total number of line segments through them would be 7 minus n times n maximum, right? And we have n line segments that pass through A, and we have already realized that there can be no other line segments like this. These are not allowed because then the triangles will be formed. So the total number of line segments is coming out to be this, which is equal to 7n plus 8n minus n square, 8n minus n square, and we can write that as n times 8 minus n, which is less than equal to n plus 8 minus n by 2 whole square by AMGM principle. The product of these two will be less than equal to this, which is actually coming out to be 16, right? We are getting total number of line segments is less than equal to 16, right? And therefore we have a contradiction, because the question itself said that the total number of line segments supposed to be 17 at least, right? So we have a contradiction, which means that our assumption that the 17 points line segments forming no triangles is wrong. We had assumed that the 17 line segments through A form no triangles. That's why we were counting the number of line segments here as simply n. Otherwise, it would be more than n, right here, if there were line segments here. So if we take it as just n, then we are getting total number of line segments should be this, which is less than 16, but 17 is given in the problem as the number of line segments. So we have arrived at a contradiction, and basically that shows that there will be a triangle formed, because when we assume no triangle, we get a contradiction, right? I hope you have understood what is happening here. We have assumed A as the point with the greatest number of line segments passing through them, and let's say n is that number. and we assume that there are no triangles formed. So the total number of line segments is n plus the remaining points are 7 minus n times n, right? That is the maximum value of the line segments, which has a maximum value of 16, and that is a contradiction. Okay? So therefore, a triangle will be formed, and a triangle usually will be formed by joining these 2 points that are connected to it. So there will be a triangle here. So I hope you understand and appreciate how we are using the extreme principle here. We are using this point A with the maximum number of line segments passing through it. Let's look at another problem. This is a famous problem. It's called Sylvester's problem. A British mathematician formulated the question, but it was not solved till 50 years later. Now we have a nice solution using the extreme principle for this problem. Let's first understand what the question says. For n points in a plane, that do not lie on the same line, show that there exists a line that passes through exactly two of these points. Exactly two of these points. So basically the problem is very simply stated. It says that there are n points in the plane that are not all collinear. They are not all lying on the same line. We have to show that out of these n points, there will be a line that passes through just two of them. Not three, not four, just two, right? Okay, so let's think about how we approach this question. So we say that since these points do not lie on the same line, each line is determined by two of these points, and it does not contain all the points. It does not contain all the other points. Basically what I'm saying is that we can find a chosen point. We can find a point outside this line. Find a point outside this line. Whenever you make a line taking some of the points, you can always find a point outside that line, right? That is true because not all of them lie on the same line. That is given in the problem. So what we will do is for each line determined by two of the points, find the distances from the outside points to this line. So this is the key step here. So I will explain with an example. So let's say we have 4 points. 4 points which are not collinear, right? Let's say we have 4 points which are not collinear. This is A, this is B, this is C, this is D. I want to say for each line determined by two of these points, how many such lines can we make? We can make 4 C2 lines, right? We can make basically 6 lines. Let's say one line is AD. So line 1 is line AD, and I want you to find the distances from the outside points to this line. So basically the distance here, this distance and this distance, right? So distance of B to AD and distance of C to AD. These are two distances. Line 2 could be what? Line 2 could be AB line. Join AB basically. And now you need to find the distances of C and D to AB, right? C and D to AB. So basically distance of C to AB and distance of D to AB, right? So basically like this, we can list out all the NC2 lines and the distances of the outside points to each of those lines, right? Outside points to each of these lines. I hope you're understanding what I'm saying. There will be NC2 lines that will be determined by these endpoints. Now, there will be outside points for each line. For each line, there are some points that don't lie on it. From those points, you draw perpendiculars and find the distances of those points to those lines. So there will be many distances. There will be many distances that will come, right? But you can easily say that the number of such distances is finite. It will be finitely many, right? Finitely many such distances, right? What we will do now is apply the extreme principle. So I will do it on the next screen. How do I apply the extreme principle? I will say there are finitely many distances so there must be a minimal distance. So there must be a minimal distance. And let's call that minimal distance as DO, right? D0. Now, suppose D0 is the distance of P to segment AB. So we draw, let's say there are 2 points AB. We have drawn a line through AB and P was here and P's distance to AB was D0, right? Correct? P was another point that was not lying on the segment AB and the distance, this was the minimal distance out of all possibilities of distances from outside points to any of the segments, right? Okay. Now let's label H as the foot of the perpendicular from P to this. Okay. Let's label H as the foot of the perpendicular. So PH is equal to D naught. So now we will try to prove by contradiction and we'll say if the proposition is not true, that means the proposition was saying that there is a line that passes through just two of these points, right? But if the proposition is not true, then there is no such line that passes through just two of these points. So then line AB must contains another point C, contains another point C. So if the proposition is not true, then line AB must contain another point C from the original set of points, right? Okay. So if it contains another point C, then we can say by common sense, at least two of the points A, B, and C lie on the same side of H, right? On line AB. So if there is a point C, then at least two of the points should lie on the same side of H, right? So without loss of generality, obviously it could lie here, it could lie here, right? Without loss of generality, we'll assume that B and C are on the same side of H and B is farther away from H. Away from H. So we'll say basically that C is somewhere here. B is the farther away point and C is lying here, right? Now what we do is construct the line PB, and we take the distance of C to PB. We take the distance of C to PB by dropping a perpendicular from C to PB. And similarly, now we can say from H to PB, we can also drop a perpendicular, and these two are parallel. And we can say that in this right angle triangle, let's call it E and let's call it D, right? We know that in this right angle triangle, D naught is equal to PH is greater than HE, right? D naught is greater than HE and HE is greater than CD, right? So we are getting D naught is greater than CD basically, right? And that just shows that the distance of C to the line joining, distance of C to line joining P and B is less than D naught. Think about it. What was D naught? D naught was the minimum distance of any point outside any line to the line segments, right? So we could have taken many points and many line segments, and D naught would be the minimum distance, right? We had assumed that D naught was the minimum distance. Here, D naught was distance from point P to the line AB. But now, if the proposition is not true, which means if there is no such line which passes through just two of the points, A and B, then that means there is a third point on the line AB, which is point C. And we have just now proved by assuming that C lies on this side, we have just now proved that the distance of C to PB is less than D naught. But that contradicts our assumption that D naught was the minimal distance. No? Now we are getting distance of C to PB is the minimal distance. This is a proof where we have constructed a situation where our assumption is now turning out to be wrong. And basically, that means our proposition is not true. So, proposition is true that the line AB cannot contain another point C. There is a line AB such that it does not contain any other third point. Because as soon as it contains a third point, we will always be able to construct a smaller distance. And that will mean that we don't have a minimal element in this finite number of integers which are distances, right? That is a contradiction. Think about it. If you have not understood, please let me know in the comments and all. But I think if you think about it carefully and go back to the video, you should be able to get it. These are three examples that we use the extreme principle in. Later in the course, we'll see more problems and more complicated situations where we will be using this principle, and we'll come back to it in many different settings. So right now, I just wanted to explain the concept and show you some basic examples. You can search for Sylvester's problem online as well, and you'll find proofs for that there as well. But this is the shortest and nicest proof that I've seen. So hopefully you like the video, and I'll see you next time.